Okay, so today we're going to talk about fats. And in order to understand fats, we need to understand a more condensed or convenient way to draw chemical structures than just by using full Lewis structures, okay? So today we're going to talk about something called skeletal structures. And we're going to start with the alkanes, and then we're going to move into fats, because fats consist of these long alkyl chains. We don't want to draw those alkyl chains out as Lewis structures. We want to draw them as skeletal structures. So here's where we start. We're going to start with like some alkanes. So here's an alkane. And then we've got Lewis structure. We're going to need a decent amount of space for that. And then we'll go skeletal structure. Okay. And let's just start with a few that we know. So we'll go with like propane. And we'll go with heptane. And we'll go with octane. And I'll actually space these out a little further because I just want to teach you how skeletal structures work. Okay, and propane has the formula C3H8, okay? And this guy's important because he's used as like camping stove gas, or sometimes as water heater gas, or even stove gas for places that can't get natural gas, which is methane. Heptane's important. It's C7H16 because it's most of the rest of gasoline, which is roughly 90% octane, which is C8H18. Okay, and drawing the Lewis structures for these things is actually a bit tedious. Because, I mean, look at what I have to do. I have to draw all these carbons. 1, 2, 3. Not too bad for propane, admittedly. Right? Not so bad. But I gotta do all this. And you can even, like, hear the rhythm of, like, what I'm drawing on the board. Somebody was, like, playing around the other day in class and, like when I was writing on the board, it's kind of a pain to draw all this. And chemists, if anything, are, like, not trying to do extra work. Like, if you're a chemist, you're saying to yourself, man, how do I work as efficiently as possible, right? So, like, I've got these structures that I have to think about, and I darn sure don't want to draw them out by hand in full more than I have to. Okay. So then, here's the last one, octane. We drew this last time, and I'm just going to ask you to draw it again because I just want you to get that tactile feel of actually having to draw the whole thing out. I promise I'm doing this for good reason. So I want you to appreciate why we use skeletal structures, because at first you might be like, man, I can't really see all the carbons and hydrogens. This is confusing to me. And so I want you to really understand why it's important to learn how to use skeletal structures, because they're way more convenient than regular Lewis structures. Like, no professional chemist wants to draw this out in any situation other than like a teaching situation or some situation in which he has to like, or she has to like talk about individual atoms or bonds. Like if you've really got to talk, okay, I really want to think about like this carbon, maybe you draw this out. But generally you won't draw this out. So I'm going to explain in words what a skeletal, first I'm just going to show you what these skeletal structures are, and as I'm doing so, I'm going to explain in words what I'm doing, okay? So, like, when you've got something like propane, right? You say to yourself, okay, propane. Propane's got 3 carbon atoms, right? 3 carbons, great. And one way I can represent propane is by like building the whole molecule itself, right? But we're humans, and humans are smart, and so humans look at things like propane, and they're like, man, I don't really have to like build the whole thing. Like, what if, and some of the scholars were like doing this last time, they were like, man, I don't want to put all of these dadgum atoms together. Like, what if I just like What if I just put like 3 of these things together and was like, hey, that's propane, and then old Dr. J comes by and he's like, no, but you got to add your hydrogens, and then the scholar's like, but no, I can imagine the hydrogens being there. Like, what if I just like think of this as propane and imagine the hydrogens there, right? Like, what if I just imagine it? That's not bad, right? Right? Like, you can imagine the hydrogens, right? Are we following? Like, you know, like I don't have to necessarily put them on there. That's not crazy, yeah. Somebody just say like, yeah. Dr. J, not crazy. On the count of 3, let's go, not crazy. If you don't think I'm crazy, 1, 2, 3.
Crazy.
Oh. No, but for real, does that make sense, yo?
Yeah.
Okay, thanks. So I agree, right? And it turns out that chemists generally agree on that topic. So they don't want to actually draw out all the hydrogens. And in fact, they don't even want to draw out the stinking carbons. So what they do is they draw out just lines to represent the bonds, okay? So like, you know what they actually represent? They represent like this guy here and this guy here, okay? They represent those 2 things. And you're like, what? And it's like, yeah, bro. Boom, boom. That's propane. That skeletal structure represents propane, okay? I, as a chemist, and you as a chemist, will look at that structure and say to yourself, okay, I've got one single line, that's a carbon-carbon bond, and there's a little kink in that line, that represents a carbon. That carbon in the middle is this carbon here. It's making 2 bonds to other carbons, and I don't draw them, I don't put them on the board, but I know they're there. It's also making 2 bonds to hydrogens. Okay? So whatever bonds it's making that are not carbon-carbon bonds, or bonds to some other atom that we would actually draw in, are carbon-hydrogen bonds. Okay? And so this guy here at the end is also a carbon atom. He's this guy. This guy is bonded to how many hydrogens? On the count of 3, 1, 2, 3? 3, right? This guy's bonded to 3. This carbon over here is bonded to how many hydrogens? 3. Good. So we don't actually draw them, but we are chemists, and we know that they are there because we understand how skeletal structures work. And we'll get more and more comfortable with skeletal structures as time goes on. So heptane, right? This guy has 7 carbons. How many lines did we draw for propane, which had 3 carbons? We had 3 carbons. How many lines did we draw? 2 lines, right? There's always going to be 1 fewer line than there will be carbons. So we got 7 carbons here. How many lines are we going to draw? 6. Good. So here we go, right? And here's how I count when I draw these so that I know I'm on track. I go, okay, I start with 1, then I go 2, 3, 4, 5, 6, 7. 7 carbons, that's heptane, okay? And you can see how much easier that is on me, right, to draw, and on you to draw, than this nightmare over here. Okay, this is a fine thing to do when you're teaching young chemists about chemistry. Otherwise, you know, most organic chemists are going to represent heptane like this, okay? It's just easier to do. And we'll all understand that this guy right here doesn't stand for carbon by itself. It stands for CH, how many? How many H's here? 3. This is CH3, right? This guy is C bonded to 2 carbons, sure, but it's also C with how many H's? 2. CH2, okay, right here, this guy, yeah, okay? CH2, 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 this one is CH3, right? Good, okay? The ones on the end by themselves are CH3. This one over here, these ones in the little kinks are CH2. That's what we need to understand for now. Now, this guy over here, octane, right? He's got 8 carbons. How many bonds will I draw? How many lines will I draw, scholars? 7, okay? Here we go. So 1, 2, 3, 4, 5, 6, 7, 8 carbons, 7 lines. 1, 2, 3, 4, 5, 6, 7 lines. So I actually count the carbon atoms as I draw, but I know that I'm only drawing 7 lines, okay? So there's that little relationship there. And that's octane. That's another way of thinking about gasoline. So what's easier, drawing out this whole thing or drawing the skeletal structure? Do we feel like that's a good thing for us to use, the skeletal structure? Is that going to save us is that going to save us time if we have to, like, let's say we had to draw, like, if you had to draw, like, C16 out, would you want to do it this way, or would you want to do it this way? Skeletal structure, right? Okay, so that's the kind of thing we actually have to deal with when we're thinking about fats. It turns out that fat molecules are made up of these long carbon chains, okay? And we're going to start thinking about fats today. So the first type of fat we're going to think about is plant fat. So plant fat, okay, and in this case, right, example, olive oil. Okay, olive oil is built like this. So you've got these three things called fatty acids, and they go on the end of a chain of a molecule called glycerol. And so, or sorry, they get attached to a backbone called glycerol. So may I erase this alkane business over here? I can erase this left half? Okay, I'm going to start erasing because I have to show you what this is all about. So I'm going to show you how plant fat comes together, and then we're going to build plant fat. And we had a really long lecture last time, and so today I think we'll just stop there, and then next time we'll start talking about animal fat. So we're just going to talk about plant fat today because I think that's good enough for today. So okay, so there are two kinds of molecules we have to understand if we want to understand what a fat is, okay? And these fats, okay, are called triglycerides. And so let's start with glycerol. Glycerol, okay? So glycerol looks like this, and I'll draw it in a few different ways. So it's C, C, C. So it's got a propane backbone or a propyl backbone, and you go H, 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 then you go OH, 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 like that, okay? So it's a triol or a trialcohol. There are 3 alcohol groups there, okay? This OH means alcohol. You might be thinking to yourself, well, wait a minute, alcohol is something that my parents drink. Humans sometimes drink alcohol. So the alcohol, I'm just going to draw this on the board and I'm going to erase it, but the alcohol that your parents drink or that adults sometimes drink is called ethanol, okay? That's also, I mean, this stuff is carcinogenic, right? It's not good to drink. And it actually is used in fuel in gasoline. So the gasoline that's in like gas tanks around San Diego has roughly 10% ethanol in it, like no joke. But this is what it looks like. So it's C2, okay, H6O. Like that, okay? So there's one alcohol group on the ethanol, on this ethane backbone, or this ethyl backbone, right? So it's 2 carbons, and then one of them is bonded to an OH group, okay? And it's that OH group that makes something an alcohol, just like you were seeing in your ACT practice today, right? There's this one little group here that makes this thing an alcohol, okay? So that's the stuff that people drink. This glycerol has 3 of those alcohol groups on it. Okay, that's why we call it glycerol. And may I erase ethanol now?
Yes.
Okay, so ethanol can go away. And a really productive way to represent glycerol is to represent glycerol actually like this. So I'm going to draw it like this. I've got my backbone, and then I go carbon 1 bonded to an OH group. Carbon 2 bonded to an OH group. Carbon 3 bonded to an OH group. This is the same as this. I have rotated it. I've rotated it 90 degrees. Is that confusing to anyone? I can redraw this top one. Are we okay with this and this being the same thing? Verlin says yes. Joanna says yes. Okay. These are the same molecule. This is the skeletal representation. This is the full Lewis structure here. You can also have fatty acids, right? So like, let's talk about some fatty acids. So like, okay, and I'm actually gonna, man, What I'm gonna do is I'm gonna erase this top glycerol and I'm gonna blow this one up. And there's a reason for this, okay? There's an absolute reason for this. So don't worry, you don't necessarily have to do this on your own, but I need to do it. So boom, so we go OH, OH, OH. Okay, so fatty acids. I'm gonna show you 3, okay? 3. And I have to always have these guys on my little note card because I gotta remember exactly how they're drawn. So here are 3 fatty acids, and here's how they look. So you go 1, 2, and you go 2, that goes at 9. So 2, 2, 4, 6, 8, 9, 10, double bond. And you go 11, 13, 14, 16, 18. Okay, this guy right here is called oleic acid. And you're like, what in the heck is an acid and why is this thing called an acid? It's called an acid because it's got this little group right here.